Today we're going to be doing section 6.2, orthogonal sets. An orthogonal set is a set of vectors u1, u2, all the way to up and Rn is called an orthogonal set if ui.uj equals 0, where I does not equal j. So let's look at example 1. Is this set of vectors an orthogonal set? So first we're going to label vectors, the three vectors, u1, u2, and u3 respectively. Then find the following. If each of these equals 0, then u1, u2, u3 is an orthogonal set. So let's find u1.u2. u1.u2 would be 1 times 1 plus negative 1 times 1 plus 0 times 0. And that would give me 1 minus 1 plus 0, which is 0. Then u.3 would be 1 times 0 plus negative 1 times 0 plus 0 times 1, which would be 0 plus 0 plus 0, which equals 0. And then u2.u3 would be 1 times 0 plus 1 times 0 plus 0 times 1, which would also be 0. Therefore, u1, u2, u3 is an orthogonal set. Theorem 4. Suppose S is u1, u2, all the way to vector up is an orthogonal set of non-zero vectors in Rn, and W span u1, u2, all the way to up, then S is a linearly independent set and therefore is a basis for W. Orthogonal basis. An orthogonal basis for a subspace W of Rn is a basis for W that is an orthogonal set. Let's look at example 2. Suppose S is u1, u2, all the way to up is an orthogonal basis for the subspace of W of Rn. And suppose Y is in W. Then C1 all the way to CP, find C1 all the way to CP so that Y equals C1 times U1 plus C2 times vector U2 all the way to CP times UP. So first, what we're going to show is vector Y dot vector U. And that would be C1 times U1 plus C2 times vector U2 plus CP times vector UP. Times U. So that would be what that would be. And then I could show Y dot U1, and that would be C1 times U1 plus C2 times U2 plus CP times UP times vector U1. And then this would equal, if I were to show this, C1 times U1 dot U1 plus C2 times U2 dot U1 plus CP times UP dot U1 And as you know, since it's an orthogonal basis, this right here would equal 0, and this right here would equal 0. So y dot u1 would equal c1 times u1 dot u1. And then what we can do is we can solve for c1, and it will give you this. So if I solve for c1, I would get y dot u1 all over u1 dot u1. And this would be y dot u1 all over the length of u1. Similarly, you can show this for c2. So similarly for c2, you would get y dot u2 all over u2, the length of u2 squared. And similarly for c3, you'd have y dot u3 and going all the way to cp, you'd have y dot up So that brings us to theorem 5. So basically example 2 showed how to find theorem. So that brings us to theorem 5. Let u1, u2, up be an orthogonal basis for subspace W of Rn. Then each y in W has a unique representation as a linear combination of u1, u2, up. In fact, if y equals c1 times u1 plus c2 times u2 plus cp times up, then cj is y times u1 all over uj times uj, where j equals 1 to p. Let's look at example 3. Express y as a linear combination of the orthogonal basis. First, label the vectors u1, u2, u3 respectively, then find the following. So to find the following, this would be, and what is missing with these is your dots. So this should be y dot u1, y dot u2, and y dot u3. So we should have 3 plus 7, 3 plus negative 7, plus 0, all over 1 plus 1 plus 0, and we get 2. Here, we should have 3 plus 7 plus 0, all over 1 plus 1 plus 0. And that equals 5. And here we should have 0 plus 0 plus 4, all over 0 plus 0 plus 1. And that equals 4. So when I express this, y would be negative 2 times u1 plus 5 times u2 plus 4 times u3. And orthogonal projections. For a non-zero vector u in Rn, suppose we want to write y in Rn as the following. y equals a multiple of u plus a multiple of a vector perpendicular to u. Y minus alpha u dot u equals 0 because of it being perpendicular. Y dot u minus alpha u dot u equals 0. Y dot u minus alpha u dot u equals 0. So we're just going and solving this. So alpha equals y dot u over u dot u. And y hat would be y dot u over u dot u times u, which is the orthogonal projection of y onto u. Z would equal y minus u dot u, y dot u over u dot u times u, the complement of vector y orthogonal to u. So y hat, the orthogonal projection of y equals y dot u over u dot u times u. So let's look at this example here. Let y equal negative 8, 4 and u equal 3, 1. Compute the distance from y to the line u, 0 and u. So this from y to the line 0 and u equals the distance from y hat to y. So this equals the distance from y hat to y. So y hat equals y dot u all over u dot u times u. So I'd have negative 24 plus 4 all over 9 plus 1 times u, which equals negative 2u, which would then be negative 6, negative 2. So to compute the distance, and since it's the distance from y hat to y, you would subtract those, and we would get, that'd be negative 6, negative 2, minus negative 8, 4. This would be the distance for vector 2, negative 6, which would then be the square root of 2 squared plus negative 6 squared, which is the square root of 40, which equals 2 square root of 10. Orthonormal sets. A set of vectors u1, u2, all the way to up and Rn is called orthonormal set of vectors. If w equals the span of u1, u2, up, then u1, u2, all the way to up is an orthonormal basis for w. Recall that v is the unit vector if v, the length of v, equals v dot v, which equals v transpose v, which equals 1. Suppose that u is u1, u2, u3, where u1, u2, u3 is an orthonormal set. Then u transpose u would equal this. And then that would equal the identity matrix. And it can be shown that u dot u transpose equals I. Also, U inverse equals U transpose. Such a matrix is called an orthogonal matrix. Theorem 6. An M by N matrix U has orthonormal columns if and only if U transpose U equals I. Theorem 7. Let U be an M by N matrix with orthonormal columns, and let X and Y be an Rn. Then the length of Ux equals X, U times vector x dot u times vector y equals x dot y, and u times x dot u times v equals 0 if and only if x dot y equals 0.